Welcome back to Fact Nexus. Last time, we explored the hidden truths of history that changed how we understand the past. Today, we're leaving Earth behind entirely. We're venturing into the cosmos to uncover 11 incredible facts about space and astronomy that will fundamentally change how you see the universe. The cosmos contains mysteries so profound and wonders so magnificent that they seem almost impossible to comprehend. But today, we're going to tackle some of the most mind-blowing discoveries that astronomers and physicists have made about our universe. So, buckle up, because we're about to launch into the infinite. Let's begin. A day on Venus is longer than a year on Venus. When we think about planets in our solar system, we tend to think about them in familiar terms. We understand that Earth rotates once every 24 hours and orbits the Sun once every 365 days. It's the basic framework we use to understand time itself. But Venus completely shatters that intuitive understanding. Here's the mind-bending truth. Venus rotates so slowly that one day on Venus, the time it takes for Venus to complete one rotation on its axis, takes 243 Earth days. Meanwhile, Venus orbits the Sun once every 225 Earth days. This means that a day on Venus is actually longer than a year on Venus. Think about that for a moment. A year completes before a day completes. If you were somehow standing on Venus watching the Sun, you would see the Sun rise, then 25 Earth days later, you would complete your orbit around the Sun and pass the same point in space. But the Sun still wouldn't have risen again from your perspective on Venus. You'd have to wait an additional 218 Earth days for the Sun to finally appear to move across your sky again. This incredible situation exists because Venus rotates in the opposite direction to most planets. It spins backwards, and it spins so incredibly slowly that its orbital period is actually shorter than its rotational period. It's one of the most counterintuitive facts about our solar system, and it demonstrates just how diverse and strange planetary physics can be. There are more stars than grains of sand on all beaches. Here's a question that seems almost unanswerable. How many stars are in the universe? Astronomers have attempted to calculate this for centuries, and the answer they've arrived at is staggering. In just the observable universe, the tiny portion of the cosmos that we can actually see with our telescopes, there are approximately 1 septillion stars. That's a 1 followed by 24 zeros. To put that number into perspective, scientists have calculated how many grains of sand exist on every beach and in every desert on Earth. The answer is roughly 7.5 sextillion grains of sand. That's a 7 followed by 21 zeros. When you compare these two numbers, the number of stars in the observable universe vastly exceeds the number of grains of sand on Earth. In fact, astronomers estimate there are about 10,000 stars for every single grain of sand on every beach and in every desert on the entire planet. What's even more mind-blowing is that this calculation only accounts for the observable universe, the part we can see. Modern physics suggests that the actual universe might be infinitely larger, extending far beyond what our most powerful telescopes can detect. So when you look up at the night sky and see a few thousand stars, which is all the human eye can perceive, you're looking at an infinitesimally small fraction of the stellar reality that surrounds us. It's a humbling reminder of our cosmic insignificance, and it raises fascinating questions about whether life exists on any of those distant stellar systems. Neutron stars are so dense, they're heavier than mountains. When a massive star reaches the end of its life, it doesn't simply fade away quietly. Instead, it undergoes a catastrophic explosion called a supernova. The outer layers of the star are violently ejected into space, creating the spectacular nebulae and expanding remnants we can see with telescopes. But what happens to the core of the star? For very massive stars, the core collapses under its own gravity to form something called a neutron star. Neutron stars represent one of the most extreme states of matter that can exist in the universe. A neutron star is so incredibly dense that if you could somehow collect a teaspoon, just a single teaspoon of neutron star material and bring it to Earth, it would weigh roughly 6 billion tons. 6 billion tons. A single teaspoon. To give you a sense of scale, the weight of a large mountain might be around 100 million tons. So a teaspoon of neutron star material would weigh roughly 60 times more than an entire mountain. If you tried to hold it, it would pass directly through the Earth, coming out the other side and continuing until it was captured by Earth's gravity somewhere on the other side of the planet. The density is so extreme that neutron stars compress the mass of our entire Sun, a star that contains 99.8% of all the mass in our solar system, into an object only about 20 kilometers across. If the Sun were compressed to the density of a neutron star, it would be smaller than a city. These objects spin at incredible speeds, sometimes rotating hundreds of times per second, and they emit beams of radiation that sweep across space like cosmic lighthouses. They're perhaps the most extreme objects in the universe, aside from black holes themselves. The Sun causes space itself to curve. Most people think of gravity as a force, invisible but real, that pulls objects toward each other. That's how Isaac Newton described it. And for most practical purposes, that model works perfectly well. But Einstein showed us something far stranger and far more profound. Gravity isn't a force at all. Instead, gravity is the curvature of space and time itself. Massive objects, like the Sun, actually bend the fabric of space-time around them. Think of space-time like a rubber sheet stretched tight. When you place a heavy ball in the center of that sheet, it doesn't pull other objects toward it. Instead, it creates a depression in the sheet, a warping of the geometry itself. Other objects moving across that sheet naturally roll toward the depression created by the massive object. This isn't merely a theoretical curiosity. The Sun is so massive that it actually warps the space-time around it. And this warping is what we experience as gravity. The planets don't orbit the Sun because the Sun is pulling them with some invisible force. They orbit the Sun because the Sun has curved the space around it, and the planets are simply moving along the straightest possible path through this curved space. This effect has been measured and confirmed repeatedly. When light from distant stars passes near the Sun during a solar eclipse, the Sun's gravity actually bends the light, changing its path. This bending of starlight was first observed in 1919 and provided the first experimental confirmation of Einstein's theory. The implications are staggering. Every massive object in the universe is creating a warp in the fabric of space around it. Earth is warping space. You are warping space. though the effect is infinitesimal. The universe is far stranger and more geometric than our everyday experience suggests. Black holes can tear apart entire stars. When you think about the most destructive forces in the universe, what comes to mind? Supernovae? Gamma-ray bursts? Colliding galaxies? But there's something far more devastating: a black hole consuming a star. Black holes are regions of space-time where gravity is so extreme that nothing, not even light, can escape once it crosses the event horizon. But black holes don't just passively sit in space, waiting to trap things. When a star gets too close to a black hole, something truly catastrophic happens. The gravitational pull of the black hole is so strong, and gravity decreases with distance, that there's an enormous difference in the gravitational force between the near side of the star and the far side. The side of the star facing the black hole experiences dramatically stronger gravitational force than the far side. This creates what's called a tidal force, the same phenomenon that causes tides on Earth, except infinitely more extreme. This tidal force literally tears the star apart. The material is stretched and pulled and heated by friction until it reaches millions of degrees. The star is shredded into a long stream of material that swirls around the black hole like water spiraling down a drain. This process is called spaghettification because the star is stretched into long, thin strands. The gravitational shear is so extreme that even atoms are torn apart. The remaining material forms what's called an accretion disk around the black hole, releasing tremendous amounts of energy as X-rays and other radiation. Some of the strongest X-ray sources in the universe are binary systems, where a black hole is actively consuming a companion star. The destruction is absolute and total. The star is completely annihilated. Nothing remains but a stream of subatomic particles swirling into oblivion. Jupiter's Great Red Spot is 3 times bigger than Earth. If you've ever looked at Jupiter through a telescope, you've probably noticed something distinctive: a large, reddish oval marking on the planet's surface. This is the Great Red Spot, and it's one of the longest-running weather phenomena in our solar system. The Great Red Spot is a storm, a massive, rotating storm that has been raging on Jupiter for at least 300 years, and possibly much longer. To understand the scale, the Great Red Spot is so large that Earth could fit inside it 3 times over. It's approximately 16,000 kilometers across, while Earth is only 12,700 kilometers in diameter. Imagine a storm so enormous that 3 Earths could fit inside it. For perspective, the largest hurricane that Earth has ever experienced, Typhoon Tip in 1979, was about 2,200 kilometers across. The Great Red Spot is more than 7 times larger than that. This storm is also far more stable than storms on Earth. Hurricanes on Earth typically last for days or weeks before dissipating. The Great Red Spot has been continuously observed for over 3 centuries. In fact, it may have been observed by astronomers as far back as the 1600s, which means this single storm might be 400 years old or older. Scientists aren't entirely sure why the storm is so stable and long-lived, but Jupiter's lack of a solid surface and its enormous size may play a role. The planet is so large that the storm doesn't interact with any land features that might disrupt it. The winds in the Great Red Spot reach speeds of about 180 kilometers per hour, and the storm rotates counterclockwise. If you were to somehow survive the crushing pressures and temperatures at Jupiter's cloud layers, watching this storm would be an absolutely awe-inspiring sight. The universe is expanding faster than the speed of light. This fact is so counterintuitive that it seems to violate everything we know about physics. Einstein's theory of relativity tells us that nothing can travel faster than the speed of light. Light is the ultimate speed limit. No particle, no signal, no information can travel faster than 300,000 kilometers per second. And yet, the universe itself is expanding faster than the speed of light. How is this possible? The key to understanding this apparent paradox is recognizing that space itself is expanding. Nothing is traveling through space faster than light. Instead, space is being created, and objects are being carried apart by the expansion of space itself. In the early universe, right after the Big Bang, the expansion was incredibly rapid. But scientists expected that gravity would slowly be pulling everything back together, like a cosmic brake. So the expansion should be slowing down over time. But in 1998, astronomers made a shocking discovery. They were measuring the brightness and distance of distant supernovae when they realized that the most distant ones were actually farther away than expected. The expansion of the universe wasn't slowing down. It was speeding up. The universe is accelerating, expanding faster and faster as time goes on. This led to the introduction of dark energy, a mysterious force that permeates all of space and is driving the expansion. We don't understand what dark energy is. It comprises about 68% of the universe, and we're essentially clueless about its nature. But its effects are undeniable. Because the expansion is accelerating, the distance between us and distant galaxies is increasing faster than the speed of light. In fact, there are galaxies so far away that their light will never reach us, no matter how long we wait. The universe has a cosmic horizon, beyond which we can never observe anything. The implications are profound and unsettling. The universe isn't just expanding, it's being torn apart. And eventually, in the incomprehensibly distant future, even nearby galaxies will recede beyond our observable universe. Astronauts can see the aurora borealis from space. The aurora borealis, commonly known as the northern lights, is one of the most beautiful natural phenomena visible from Earth. On clear nights in high northern latitudes, you can see curtains of colored light, greens, reds, purples, dancing across the sky. It's a breathtaking sight that has inspired wonder and superstition for thousands of years. But what astronauts see from space is even more spectacular. The aurora is caused by charged particles from the sun colliding with gases in Earth's atmosphere. When solar wind, a stream of charged particles constantly flowing from the sun, reaches Earth, it interacts with Earth's magnetic field. The magnetic field channels these particles toward the poles, where they collide with oxygen and nitrogen molecules in the upper atmosphere. These collisions excite the atoms, causing them to emit light. From the surface of Earth, we see this light as colorful curtains. But from space, astronauts see something different. They see the aurora from above, and instead of curtains, they see vast, luminous ovals surrounding Earth's magnetic poles. These auroral ovals are hundreds of kilometers across and glow with intense, almost otherworldly colors. They're constantly shifting and changing, creating a dynamic light show that astronauts describe as absolutely mesmerizing. What makes the view from space even more dramatic is that astronauts are watching in real time as charged particles from the sun interact with Earth's magnetic field. They're seeing the immediate consequence of solar activity. During strong solar storms, the auroral ovals expand and intensify dramatically. Astronauts have reported that watching the aurora from space is one of the most profound experiences of spaceflight. It gives you a visceral sense of Earth's place in the solar system and the constant interaction between our planet and the Sun. The colors are more vivid than any photo can capture, and the sheer scale is difficult to comprehend until you see it with your own eyes. Saturn's rings are made of billions of icy particles. Saturn is famous for its rings. They're perhaps the most visually distinctive feature of any planet in our solar system. For centuries, astronomers could see the rings through telescopes and marveled at their perfect structure. But what are they actually made of? Many people imagine Saturn's rings as solid structures, like the rings of a tree or a hoop made of rock. The reality is far more interesting. Saturn's rings aren't solid structures at all. They're made up of billions upon billions of individual particles, ranging in size from dust grains to objects many meters across. The particles are composed primarily of water ice, with some rocky material mixed in. The rings were probably formed when a moon orbited too close to Saturn and was torn apart by tidal forces, or when a comet or asteroid was captured and destroyed by Saturn's gravity. The individual particles in the rings are in constant motion, orbiting Saturn at different speeds depending on their distance from the planet. Closer particles orbit faster, while more distant particles orbit slower. This creates a complex system of interactions where particles are constantly colliding with each other, transferring momentum and energy. Despite these constant collisions, the rings maintain a surprisingly stable structure with distinct bands and gaps. The Cassini spacecraft, which orbited Saturn for 13 years, discovered that these gaps are carved out by the gravitational influence of Saturn's moons, which pull on the ring particles and create regions where particles can't easily maintain stable orbits. The rings are remarkably thin. Despite being hundreds of thousands of kilometers in diameter, the rings are estimated to be only about 20 meters thick in most places. If Saturn were the size of a marble, the rings would be thinner than a sheet of paper. The rings are constantly changing. Over time, ring particles gradually spiral inward and are consumed by Saturn's atmosphere. New ring material is probably being created by collisions between larger particles. Saturn's rings might be relatively young, only a few 100 million years old. Or they might be billions of years old. Scientists are still debating the origin and age of the rings, but all agree that they represent one of the most beautiful and complex structures in our solar system. The first picture of Earth from space changed everything. On December 24, 1968, the crew of Apollo 8 orbited the Moon and took a photograph that would change human consciousness forever. The photograph showed Earth rising above the lunar horizon, a blue marble suspended in the black void of space. It's called Earthrise, and it's arguably the most important photograph ever taken. Before this image existed, most people had never seen Earth as a whole. We lived on a planet, but we had never truly seen it. We knew Earth as a collection of countries, continents, and landscapes. We understood it through maps and descriptions, but we had never seen it as a unified object, a single world floating in the cosmic ocean. The Earthrise photograph changed that instantly. It showed Earth not as separate nations or continents, but as one interconnected world. It showed how small our planet is in the context of the solar system. It showed Earth's fragility, a thin atmosphere, a delicate biosphere, surrounded by the hostile vacuum of space. The impact was profound. The photograph became an icon of the environmental movement. People looked at this image and suddenly understood, viscerally, what they had only understood intellectually. We all live on the same planet, and that planet is precious and finite. The photograph influenced the creation of Earth Day in 1970. It influenced environmental policy and philosophy. It influenced how people understood their relationship to the planet. Perhaps more fundamentally, the photograph influenced how people understood their identity. We weren't primarily Americans or Russians or Africans. We were Earthlings, inhabitants of a single world. The Earthrise photograph demonstrated that space exploration isn't just about reaching other worlds. It's about changing how we see our own world. Many of the astronauts who saw Earth from space reported profound personal transformations. They spoke of developing a new appreciation for Earth's beauty and fragility. Some scientists call this the overview effect, a cognitive shift that occurs when people see Earth from space and recognize that planetary boundaries are real and that all of humanity shares the same home. We've only explored 0.0001% of space. Here's a sobering thought that will give you perspective on human achievement and cosmic reality. People often say that we've explored more of the moon than we've explored of the deep ocean. It's a striking statement because it highlights how vast and inaccessible the ocean is. But here's something even more striking. We've explored infinitely less of space than we've explored of the ocean. To understand the scale of space exploration, consider this. The farthest human-made object is the Voyager 1 spacecraft. Voyager 1 was launched in 1977 and has been traveling through space for nearly 5 decades. It's currently about 24 billion kilometers from Earth. That sounds incredibly far, but it's actually less than 1/10,000th of the distance to the nearest star. The nearest star, besides our Sun, is Proxima Centauri, which is about 40 trillion kilometers away. Voyager 1 would take about 80,000 years to reach Proxima Centauri if it were traveling toward it, which it's not. And Proxima Centauri is just one star among an estimated 2 sextillion stars in the observable universe. We've sent probes to all the planets in our solar system. We've landed on the moon, on asteroids, on Mars. We've accomplished remarkable things. But all of this exploration has only touched the tiniest fraction of nearby space. If you were to imagine the observable universe as a sphere and color in the portion that we've directly explored, you would need a microscope to see the colored region. We've photographed galaxies that are billions of light years away. The Hubble Space Telescope has revealed the existence of hundreds of billions of galaxies. But photographing something is not the same as exploring it. We can see these distant places with light and radiation, but we can never physically reach them. The speed of light itself is the ultimate barrier. At the speed of light, it would take millions of years to reach the nearest galaxy, and nothing with mass can actually reach the speed of light. The universe is so incomprehensibly vast that human exploration will forever remain confined to a negligible fraction of it. It's a humbling reality that shows us just how limited our perspective truly is.